So we need to think about what the bandwidth of a pulse stream is. When we were describing analog modulation, we sort of naturally talked about it as a spectrum or a series of frequencies that created our signal. But when we talk about digital modulation, we're thinking more about just a stream of ones and zeros or pulses. And we know that a square pulse in the time domain extends as a sinc function in the frequency domain, and that the bandwidth in the frequency domain, if you will, is tied to the period here, TB, ties directly right here to the bandwidth. But you notice this really isn't our bandwidth because we've got all of this other stuff here. And this is because the sharp transitions that occur in, if you think about an ideal bit stream, actually turn into an infinite bandwidth, which is a real problem because the spectrum as it is now is very crowded. And if you think about the olden days with FM radio, you know, the reason you couldn't put more stations on the dial was because you needed a certain amount of space between them because their bandwidth was a certain size. If each one of those started transmitting a digital signal, they would overlap over all of them nearby. So for digital modulation, we've got to figure out some way to fix this modulation bandwidth creep. So let's take a look at the bandwidth of a binary phase shift key. So we've got our digital pulse stream down here on the left, and we've got our cosine. And if we're multiplying in the time domain, we just do a convolution in the frequency domain. And we end up with the spectrum shown here. And as I said, we can't transmit all of this extra amount that we'd like to. And so you might think, as I would have thought initially, that this is no problem. Let's just come in here and let's just do a filter, right? That just gives us the center lobe and we'll just get rid of this back lobe. And if we looked at that in the frequency domain, that would solve our spectrum problem. But the question is, if we just put a filter like that in, what would it do to our time domain signal? This is where the idea of inner symbol interference comes in. So we need to limit the bandwidth of the baseband signal. And what happens if we just do the filtering I mentioned? We just go in and we get rid of this. Well, what we do is we end up just smoothing out each pulse. And that in itself isn't a problem, but the pulse gets smoothed out and it kind of spills over onto the next pulse. And so what you have is at this point in time, you've got not only the response from the pulse you care about, but you've got all of this energy from previous pulses kind of spilling in here and causing interference. Because remember, each unit of time, we're transmitting a symbol. And remember, that symbol can be a single bit, it could be 2 bits, it could be 3 bits, whatever it is our modulation scheme is. We continue to transmit at the same rate. We get higher data by having higher complexity modulation. So in this time t, we get this spillover, and we don't know if the signal we're receiving is due to the current signal or due to what came before this. And as each pulse spills in, it's what we call inner symbol interference. And it results in distortion and ultimately in error in the detection of the signal.